So this PowerPoint slide deck here that I'm going to roll through is the answers to the warm-ups. I hope you tried them before you watched me do this. Some of them might throw you off. Others you might be able to sail right through. The first couple questions, a lot of kids don't know what to do with number one, which is totally fine. But then they never look at number two, which is horrible. I am positive you can do number two. But first, let's talk about number one. So these two graphs are called mass specs. And what a mass spec is when you take a compound like the one you see, right here, you take a compound and you run it through a machine that breaks it apart into pieces. And just imagine cutting bonds and how there'd be different mass pieces left over all over the place. And so that's what's going on there is that they're chopping it up. Um, and you could look at the changes in mass and kind of take a guess as to what piece was chopped off. So the first one has a molar mass. So it looks like it's 98 because that's just about the biggest. There's also a 99 in there, which has me kind of wondering a little bit. And then the second one's big peak, not that tiny one, but the largest mass big peak is 45. So those are probably the two molar masses, 98, 45 for these two molecules. Now, for the one on the left, we also have the Lewis diagram, so we're going to be able to figure out a lot more about that one. And then we're going to do some follow-up things with the one on the right and question two. So, what do some of these peaks mean in the one on the left? Well, let's compare the first two big masses, 98 and 83. 98 and 83, that's a difference of 15 grams. And then what in this molecule could be 15 grams heavy? Carbon and three hydrogens. That's 12 plus 3 is 15. And you notice there's several CH3s. And so any one of those three could be broken off. And that's probably why we're getting such a big peak here. It's representing the possibility that this one is gone, this one is gone, or this one is gone. And so as this gets run through a mass spec and gets chopped to pieces, one of the biggest examples might be just taking one of the CH3s off, which is why we see the drop of 15. Let's look at another drop from 98 to 45. That's a drop of 43. The 43, that most likely corresponds to CH3COO. So what I did is I just figured out I had already chopped it here once. Maybe if I chop it here, and then I add the pieces together. CH3CO is that difference, that 43 peak. And I'd like to point out that we're also seeing the 43 peak here. That is that same piece, right? That is that same piece. And so each of these peaks represent different possible slices and dices of this molecule. What about the other one? Well, we have a high peak of 45 and then a high peak of 44. That's a difference of one. Maybe they're cutting some hydrogens off. Could be a lot of hydrogens to cut off. And then 45 minus 28 is 17. Huh, 17. That's not a terribly good number. If I look at the periodic table, there isn't an element 17, but there's carbon with oxygen. There's carbon with a couple oxygens, maybe oxygen with a hydrogen. There could be a couple combinations. Let's look at the next question. Okay, we have a sample that contains 53% carbon, 15% hydrogen, 31% nitrogen. What is its empirical formula? So I'm not showing all the work here. You should be able to do some of this, but I'll explain it. First, I did mass to moles, divide by the smol, get to whole. Hope you remember that. But so I took the 53 grams of carbon, I converted it using the periodic table to moles. I did the same thing with hydrogen. I did the same thing with nitrogen, dividing by their molar masses. Now I have all three given pieces of data in moles. And if I divide that by the smallest, mass to mole, divide by smol, divide them all by the smallest, and I get 2, 7, and 1. And those are nice, close to whole numbers. I think the hydrogen was 6.99954, so I rounded that up to 7. I didn't feel bad about that. But all three values were very close to whole numbers, so I went with C2H5N as the empirical formula. And then the next part was compare it to a molar mass of 45. And you see that the molar mass of C2H5N is 45.1. Wow, that's a pretty good match. So then I drew the Lewis dot structure that you see here. CH3, CH2NH. There is also a possibility of putting the nitrogen in the middle and moving some things around there. I wasn't too keen on that because I wanted to have something close to 17 because that was one of those main breaking points. And CH3 is only 15, or at least 14 plus 2 is 16. That's closer. 3, 4, and 5, what's the molecular geometry of the central carbons? They're tetrahedral while the nitrogen's trigonal pyramid. What's the hybridization? Well, they're all sp3. Is it polar or nonpolar? It's definitely polar and would have hydrogen bonding because of those NH2s on it. Is this molecule soluble? Yes, yes, it is soluble. Things with hydrogen bonds are attracted to each other. Water has hydrogen bonds. This molecule has the potential for hydrogen bonds, so they should be soluble inside of each other. And what type of solid would they form? It would form a molecular solid. Solids are formed from like atomic solids, molecular solids, covalent networks, that sort of stuff. And since these are individual molecules connected together with hydrogen bonding, and that would be molecular solid. It would have hydrogen bonding as the main component, and then of course dipole-dipole and London dispersion forces. If you had 22 grams of this compound dissolved in 250 milliliters, what's the molarity? And it specifically said no calculator. So you should be able to do some of this math without a calculator. The numbers are generally rigged on the multiple choice, just like this one is. So CH3, CH2, NH, 12 plus 3, 12 plus 2, 14 plus 2 is 45. Then they give you 22 and a half. Well, that's half of 45. So you have half a mole of this molecule. And then if you take half a mole and divide it by a fourth of a mole, 50 divided by 25 is 2. So it's a 2 molar solution. Then there was a chart where you had to fill a bunch of stuff in. I did not fill in the valence electrons or Lewis structures. It was just going to be tedious for me to draw. I think you can see this one in your head. This one, sulfur has 6 electrons, but it's got 4 bonds here. There must be an extra pair on top. You've seen carbon dioxide 100 times now, and nitrogen in the middle with 3 bonds and an extra pair. So I filled all these pieces in. Let's skip down here. What type of solid? Each of these are molecules, so they'd be molecular solids. This is held together covalent, 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 covalent. And then between molecules, how would they be held together? Well, if they're polar, they might have a dipole moment. This one has hydroxides on it, so it could also do hydrogen bonding in addition to being polar. This one's just CO2, so it's going to have London dispersion forces. So then we have their molar masses, which just added it up. And since this one's hydrogen bonding, it should be the hardest to break apart. It should be the most, the strongest intermolecular force there. So I would guess that that one's going to have the highest boiling point. And then I was really stuck between NCl3 and SF4 as to who would be the second highest. And so then I compared their masses. Since they're both dipole-dipole, I didn't have much to go on there. But the mass of 108 versus 120, I think that the one that's 120 would be higher. I accidentally skipped forward. The one thing I'm definitely sure about is that CO2 would have the lowest boiling point, meaning it would be the easiest to break apart. Keep in mind when you're thinking about boiling point, you're thinking about how hard is it to separate the molecules into separate molecules. So you have a CO2 and a CO2, and they're bonded together, and you're trying to break them apart. Well, since CO2s are bonded with London dispersion forces, which are really weak, it shouldn't be hard to break them apart. On our next slide, we have a whole bunch of different combinations of elements. We're just to figure out what type of solid and all the different properties we're supposed to know. So this is a metal and a nonmetal, so it'd be ionic. Yes, it would dissolve in water using ion dipole attraction. Would not conduct electricity. Wouldn't conduct electricity as a solid, and it would have a very high boiling point because it's an ionic solid and they're held together with strong electrostatic forces. CH4 is a molecule. It is nonpolar, so it would not be dissolvable, would not dissolve in water, would not conduct electricity, and at low boiling point, because it's nonpolar, it would be very easy to break CH4s into separate molecules, or also known as gases or stuff. Tin is one metal, it would have metallic bonding, it would not be soluble in water. It would conduct electricity because it would be a sea of free-floating electrons. So that's how we describe metals. Its boiling point would be pretty high, probably in the thousands. SiC is one of those network solids where they're all covalently bonded together. It would not conduct electricity because everything's stuck inside the covalent bonds. And covalent bonds are hard to break, so its boiling point would be insanely high. Neon is a noble gas, so it would have just one type of atom, so it would be atomic bonding, very weak bonding, London dispersion forces only. It would easily turn into a gas. Easily. It's very low boiling point, and it would definitely not conduct electricity. Molten sodium chloride is not a solid, but it would have ionic bonding in the liquid phase. It would be dissolvable in water, but it would be super hot. So that's kind of a silly question because it would boil the water. Yes, it would conduct electricity if it was molten because the ions can move, and it would have a very high boiling point. And then sucrose is one big molecule. This is a sucrose molecule. It's pretty big. Yeah, it would dissolve. It would dissolve in water. It's got lots of hydroxides. But no, I had to get a drink. Sorry. No, it would not conduct electricity because there's no free moving electrons, no free moving ions. Everything's covalently bonded. What's its boiling point? You know what? I think that's a bad question. I don't think it would really have a boiling point. I think it would break down in some way. It's difficult to boil sucrose. Anyone that's done any candy making knows that as you warm up sugar, it will melt, but eventually it may scorch. And that means you're actually burning it and it's breaking down. Big organic molecules like this don't always have a boiling point when they're complicated. Oftentimes they have a point at which they just break down and become smaller compounds, meaning they're reacting. All right, this is already warm up number 3. I'm doing great. Which one of these is amorphous and crystalline? Crystalline means highly organized, amorphous means not, so obviously that one's amorphous. Rank these from lowest to highest boiling point. I did. Hydrogen and fluorine are both nonpolar, so they should be first. Hydrogen's lighter, so it's first to first. HCl is just a dipole, so it's next. Then we have hydrogen bonding, then we have ionic, stronger ionic, and covalent. Notice that I said ionic and stronger ionic, as I really want to emphasize this, that potassium's +1 is attracted to chlorine's -1. If you throw that into Coulomb's law, you have a 1 and a -1. Where aluminum is a +3 and sulfur is a -2, that's going to be a stronger attraction, a stronger force. Maybe 3 times 2 is 6. That's a stronger force between those ions. So aluminum sulfide should be harder to break down than KCl. Identify the type of bond or intermolecular force between the following. I went ahead and wrote it down. You have to read these carefully. I screwed up the first time it was about halfway through before I realized I was not reading carefully. Like A says iodine and iodine in an iodine molecule. That's one within one iodine molecule. They're held together by covalent bonds. You draw an iodine, another iodine, they share 2 electrons. That's a covalent bond. Sodium and chlorine in a solid sodium chloride. They're connected by that Coulombic attraction where positives and negatives attract, which we call ionic bonding also. HBr and another HBr, that would be a dipole to a dipole. NH3 and another NH3, that would be hydrogen bonding with nitrogen, oxygen, or fluorine. H and F in a HF molecule. This is the one where I finally realized I was doing the others wrong before. H and F in a molecule, that's covalent. You have to draw a Lewis dot structure and realize they're sharing 2 electrons. Between bromine and another bromine molecule, they're both nonpolar, London dispersion forces. Copper and zinc atoms and brass. That would be metallic bonding between two water molecules, hydrogen bonding H and O in a water molecule. They're covalent, they're sharing electrons. Carbon and carbon in a diamond, they are covalent as well. I did not do a great job drawing these. I apologize. I was having trouble on my screen. With the gas, you want to make sure you show they're separated. The hydrogen bonding, you need to kind of indicate in some way that there's a connection between the hydrogen on one molecule and the oxygen or fluorine or nitrogen on another molecule. With the NaCl, you kind of have to put them in an arrangement, positive, negative, positive, negative. And with the iron, you have to show those extra electrons kind of floating around on the outside, showing that sea of electrons. NaCl dissolved in water. The sodium ion should have the oxygens oriented towards it, where the chlorine ion should have the hydrogens oriented around it. Again, I didn't do a great job drawing. I have trouble drawing on my screen. Sorry about that. But you kind of see how the hydrogens are close to the chlorine, where the oxygens are close to the sodiums. And now that I'm saying this all out loud, I realized I didn't add the dots around the oxygens to complete the Lewis dot structures. That was also my fault. In the hydrochloric acid, we have chlorine next to hydrogen, chlorine next to hydrogen, chlorine next to hydrogen. All right, what are we looking at here with this graph? Well, we're comparing the boiling points of a whole bunch of simple molecules, small molecules. And let's start with group 4. We see it slowly increasing in boiling point as we go from the second, third, fourth, and fifth period. So why would there be this slow increase? Well, all 4 of those molecules we would assume are kind of tetrahedral. They have more and more electrons, but they're still tetrahedral. So why are we seeing this increase? Well, not only are they have more and more, uh, are they the same shape, tetrahedral, but the tin has 4, 5 energy levels. The germanium has 4 energy levels. Silicon has 3 energy levels. Carbon only has 2. And so what we're really seeing here is as they add more and more electrons around an atom, those molecules become more polarizable. That's where the electrons can be more easily shifted because there's a greater number of electrons. And we're seeing that in this group. We see the same thing in groups 6, 5, and 7 with the huge exception of group 2. And I think you already know what's going on in group 2. We have hydrogen attached to oxygen, fluorine, and nitrogen. And we've talked about hydrogen, fluorine, and oxygen and nitrogen. I said that out of order. But those 3 elements with hydrogen ad nauseum, they can form stronger than predicted bonds, and we call those stronger intermolecular bonds hydrogen bonds. But aside from those hydrogen bonds, we are seeing the same trend as there's more and more energy levels, the boiling point goes up. These molecules, we have PET and HDPE. Um, PET and HDPE are obviously very different, and we're supposed to kind of like figure out what's going on here. But first, before we really look at these too closely, let's look at the data we've been given. We're given the softening point and the melting point of these 2 molecules. That melting point for PET is drastically higher. I mean, I wouldn't say double because these are probably Celsius, and Celsius is not the proper scale for saying double. Um, but it's 130 degrees higher. So that means the forces holding it together must be stronger. And so as we look at these, we're kind of looking for what would cause the PET molecule to have stronger forces than the HDPE molecule. Ooh, this is a mouthful to say. Um, so the PET, you can see a lot of NH to O, NH to O, NH to O, NH to O. That hydrogen is trapped in that tug of war match between the oxygen and the nitrogen every single time. So the PET has lots of hydrogen bonding. Well, it brings us back to the other side here with the polymer HDPE. Why is this even got a high um, melting point at all. 130 is higher than water. It's a very long molecule. It doesn't actually end here. It keeps going. Neither one of these end. It's just huge, long strings of molecules that might be thousands of carbons long or thousands of these cyclic rings long. And uh, the only reason it's even got a high boiling point is because these molecules would be polarizable. But there is not going to be a strong force between the two. This is only going to have London dispersion forces due to the polarization of the molecule. What did that mean? The electrons could be shifted one way or shifted the other way, and then they would be attracted to the other molecule. And then we're supposed to say, hey, here's nylon. Nylon, which would it be closer to compare to? And you can see that you've got that same oxygen, nitrogen with the hydrogen trapped in between. So it's going to be a lot closer in melting point to the PET than the HDPE. Whew. Again, those are mouthfuls. I do like showing these because you probably know what nylon is. You see nylon in clothes and things like that. And you can see like it's a carbon, hydrogen. There's a 4 there, so that's actually CH2, 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 CH2. There's 4 of them in a line. Chuk, 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 chuk. And then this carbon double bond, nitrogen, hydrogen. And then look, there's I think that says 6. It's kind of blurry. And then 4 and 4 and 6. And this repetitious pattern is the polymer that is nylon. And that nylon is originally made through harvesting from. Wait, no, I was going to go in the wrong direction. Nylon was kind of one of the replacements for silk at a certain point. Nylon was invented, I think, in the 1920s or 1930s. Um, it's acrylonitrile. Yeah, I'm not going to remember all the little details about making nylon, but it's pretty cool. Um, so plastics and polymers. There's different types of plastics. There's thermosets, and then there's the ones that are more recyclable. And the two plastics have very different properties. The ones that are like stuck in their form and can't be reused versus the ones that can be recycled again and again and again. And so you're actually seeing two of those here kind of at the molecular level. The one on the left is the harder type of plastic because what's connecting the different strands of polymers are covalent bonds. And as you know, covalent bonds are very difficult to break. So that polymer on the left, it's really like one giant molecule because everything's connected. And these are your harder plastics with almost no flexibility whatsoever to them. They crack first. Um, Whereas with water bottles and other flexible plastics, there are weak intermolecular forces between the polymers. And that's what the drawing on the right is supposed to show. I think those on your paper look a lot more like dashed lines, and they're hydrogen bonds. And hydrogen bonds are weaker, so those little strings, those polymer strings, can slide past each other. And so often the ones on the right are called thermosets because if you warm them up, those hydrogen bonds will break and the molecules can slide past each other. And when they recycle these plastic water bottles and things, they heat them up till all those hydrogen bonds are broken. And they can pour the liquid plastic into whatever form they want. And if they cool it down slowly, the hydrogen bonds will form and it'll keep whatever the new form of the plastic is. And so thermosets are based off of the concept of weak intermolecular forces. Number 8, when sodium chloride dissolves in water, we have these ions, and the force that exists between them is called an ion dipole interaction. Water is a dipole. It's got a positive side and a negative side, and of course, these ions are attracted to that, which we've hit that a number of times. In 9 to 12, we have to like read this sentence that describes the properties of the solid and kind of eliminate what might be described. So we're going to read through this description and then look at number 9. So we have a solid that's like a poor conductor of electricity. It's very hard, it has a high melting point, and it's not brittle. So let's see what choices we can eliminate. I've obviously underlined the answer, but let's eliminate the others. So molecular solids do not have high melting points. Molecular solids have low melting points. They break apart often way below 0 Celsius. So it's not a molecular solid. Ionic solids don't conduct electricity at all. Um, they don't conduct electricity unless they're molten. The other thing is that ionic solids are very brittle. If you hit an ionic solid, every atom shifts a smidge and it pops open. Metallic solids, well, they are not brittle. They're malleable. They are very hard. They do have a high melting point, but metallic solids are good conductors of electricity, so it can't be that one. The network covalent, these are your diamonds, your sand, things like that. They don't conduct electricity well because it's all covalent. They are very hard because it's only covalent bonds. They have high melting points because since it's covalently bonded, the energy can be distributed very well. And they're not brittle because of the covalent bonding. They tend to pass energy around throughout the entire thing. Remember, with a network covalent, it's like one giant molecule, one huge covalent bonded molecule. Pick an example. So you're supposed to know the different things that what categories they would fall in. Si2 is a covalent solid. I mean, a network covalent. Tin would be metallic. Rock salt would be ionic. And table sugar would be a molecular solid. They even give you the formula for a molecule. This another one. SiC is also a network covalent. I said in the notes you need to go through and you have to know the couple of examples listed in there. SiO2, carbon as diamond, carbon as graphite, SiC. There weren't but a couple. And the property of this solid can be attributed to an interlocking pattern of atoms. Every single atom in there is covalently bonded to every other atom in there. Almost done. Which of the following will have the greatest electrical conductivity? We're looking for the one that's the best metal. If it's conducting electricity, and these are just elements, phosphorus is definitely a non-metal. Arsenic and silicon are right on the edge, but gallium is not. Gallium is a straight up metal. I would pick gallium. Electrostatic forces of attraction are greatest in which of the following? Ooh, I like this one. So electrostatic forces, that's Coulomb's law. So what's Coulomb's law? F equals K Q1 Q2 over D squared. So let's check the charges. Plus 1 minus, no, plus 2 minus 2, plus 2 minus 2, plus 2 minus 2, plus 2 minus 2. So the charges are not what we're looking for. So we're going to focus on the distance. So the distance between the ions is determined by their size, and we can kind of get a general sense of their size by finding their location on the periodic table. Let's compare oxygen to sulfur. Which one would be smaller? Oxygen would be smaller. It's on the second period of the periodic table, so it would be smaller than sulfur, which is on the third period of the periodic table. So that gets us down to choices A or B. Now, what about magnesium and barium? Which one is smaller? Magnesium. So B, magnesium oxide is going to have the greatest electrostatic force because those two atoms, scratch that, those two ions have the greatest electrostatic attraction between them based off of Coulomb's law, F equals K Q1 Q2 over D squared. Okay, so we have four choices. We have to figure out which ones could apply here. I haven't actually thought about this, so there's going to be a lot of me talking out loud. Um, which one would have the highest melting point? Germanium, glycerol, lithium chloride, or propane? Okay, so we need to analyze those four substances and kind of set our mindset clearly. Germanium is a metal. Um, and so they're going to be tightly bound, but oh, look at that description. It's a solid where the atoms are bound to each other, much like those of carbon and a diamond. So they've just said that's a network solid, network covalent solid. All right, I should have read these thoroughly. Glycerin, glycerol. Glycerol is an alcohol. Look at those hydroxides on there. I think I see some hydrogen bonding. Lithium chloride, LiCl. That's an ionic compound. Be strong ionic compound forces. And then propane, C3H8. That's a gas. It is a molecular solid or molecular. It's a molecule, but not a solid right now. So it clearly says it's a gas, goofball. Okay, which one has the highest melting point? Okay, based off my actually reading these questions, I would say germanium with the covalent bonds, kind of like carbon, would be the highest. Lithium chloride would be the second highest. Then glycerol would be third, and propane would be the worst. It would have the lowest melting point. The greatest hardness in the solid phase. Again, germanium is going to have the greatest hardness. It's going to have the strongest forces, followed by lithium chloride. The lowest heat of vaporization. Oh, we got to figure out what that means. Heat to vaporize something. How hard is it to vaporize? But which one's the easiest? It's going to have the lowest. Oh, so which one is the easiest to vaporize? Da, 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 da. That's got to be D. Propane would be the easiest to turn into a vapor or gas because it's got the weakest forces. Conductivity is fused or melted state, but now in the solid state. Conductivity in the fused or melted state, but now in the solid state. I think they're talking about lithium chloride there. I'm not sure about the fused, but the melted state, lithium chloride, the ionic compound, could conduct electricity, but the others couldn't. And then we already talked about hydrogen bonding and glycerol. The last slide. Heck yeah. Molecules in a sample of pure liquid dichloromethane. That's a fun one to say. Dichloromethane. That's CH2Cl2. Draw that Lewis dot structure. Then after you draw it, realize that it's tetrahedral, and therefore those hydrogens and the chlorines aren't really across from each other. They're at a 109-degree angle, right? Okay. So if they're not really across from each other, then it's going to be a dipole-dipole. Not going to be hydrogen bonding because you don't have the other three elements required. And it would definitely have London dispersion forces. So it's going to be I and II. That is C. And lastly, let's finish strong on 21. The molecules in a sample of SO2 are attracted to each other by a combination of, draw the Lewis dot structure for SO2. It clearly says it's a molecule. That'd be sulfur, 6 electrons, oxygen, 6 electrons, oxygen, 6 electrons, double bond, double bond. Sulfur would be bent, angular. I prefer to say angular. So the sulfur would be angular shape. That means it's going to have a dipole. It does not have hydrogen in it, which is kind of key to having hydrogen bonding. So it can't be any one of the choices with hydrogen bonding. And if it's a molecule, it always has London dispersion forces. So D is the correct answer. You've done it again. You've listened to me yammer on about molecules, bonding, solids, and liquids. I hope you're having a great day, and I will see you all in the future.